If you've been following the world of AI agents, you know they're quickly becoming, well, incredibly powerful tools.
They really are.
But there is this massive bottleneck, a really fundamental challenge that separates a truly sophisticated agent from what is, just a very fast data cruncher.
Memory.
Memory. It's all about managing this overwhelming amount of context and historical data. We often bring up Albert Einstein when we talk about this, and the source material for this deep dive quotes him directly.
Oh, I know the one.
Intelligence is not the ability to store information, but to know where to find it.
And that quote it perfectly encapsulates the problem we're seeing. These agents, driven by LLMs, they struggle not just with the sheer volume of data, but with finding the precise information they need for a complex task right at the exact moment they need it.
So that's what we're digging into today.
It is. This deep dive is all about analyzing a new framework designed to solve this exact problem, the General Agentic Memory, or GAM for short.
Okay, let's unpack this then. Our mission today is to really understand how GAM re-engineers the way agents manage information, shifting from that traditional, often brittle, static approach to something entirely dynamic.
We'll get into how GAM makes that transition to what's called a just-in-time, or JIT, model. And to do that, we have to look closely at its specific dual architecture. It uses two specialized agents.
And then the results, I assume?
And then we'll review the rigorous experimental results.
Mm.
They really validate its performance across some very challenging memory-grounded tasks. We're talking benchmarks like Locomo, Hotpot QA, and Ruler.
Right. But before we get to the solution, we really need to define the problem. If GAM operates just in time, what have agents been using up until now?
The current widely adopted standard is what researchers call ahead-of-time compilation, or AOT.
Ahead of time.
Think of it like pre-planning every single step of a huge research project before your client even asks the first question. In this offline stage, the system does a massive amount of computation to compress the entire raw context into a lightweight fixed memory structure.
And then all the future questions are answered from that summary.
All subsequent requests are served based primarily on that pre-constructed condensed memory.
And if you're compressing all that information ahead of time, what's the core danger there?
Well, the first and most critical danger is just information loss. Memorization is, by its nature, a form of data compression, so that pre-computed memory inevitably sheds detail.
So if a later request needs something really specific,
It's gone. If a request comes in that needs a fine-grained, highly specific piece of historical information, that compressed memory often simply can't provide it.
it sounds like the system is sacrificing fidelity for speed. And if that memory structure is fixed, that also introduces inflexibility, doesn't it?
Oh, absolutely. AOT systems usually assume a static structure. So if an ad hoc or, an unforeseen request comes in, something the system wasn't initially designed to categorize, the agent really struggles to adapt.
It's constrained.
It constrains its ability to generalize across different tasks because the memory was organized based on a predetermined, often handcrafted set of rules.
So the system is trying to answer these really nuanced questions using just a fixed summary, which I think leads us to the core philosophical shift of GAM.
It does.
Instead of trying to cram all the context into a lightweight memory, the goal is to keep the complete history available.
Exactly right. The big insight behind GAM is that true lossless memory requires searching over a complete, pristine history database. The lightweight, pre-computed memory should only be introduced to support and to guide that comprehensive search process.
Never to replace the raw data.
Never to replace it.
That makes perfect sense. So GAM embraces this principle of just-in-time compilation. Instead of trying to predict what the client will ask and building a summary, JIT focuses on building optimized context for the client at the moment of the request.
While keeping only the simplest, most useful guides offline. And that JIT principle is realized through a novel dual architecture. Two specialized LLM-based agents. They're called the memorizer and the researcher.
Okay, let's start with the memorizer. It handles the continuous stream of incoming history, right? The sessions the agent has. What does this memorizer actually do in its offline stage?
It's doing two things at once. First, there's memorizing. It dynamically compresses the key historical information from a session into a lightweight structure they call a memo.
A memo, like a little note.
A concise, well-structured snapshot.
Hmm.
And it incrementally updates the agent's overall memory structure. This is that simple guide we were just talking about.
And the second action is where the complete history is protected. The paper calls it paging. This seems crucial to avoiding that information loss problem of AOT.
It's the linchpin of the whole system. Paging means the memorizer merges the raw session data with all its necessary context to form a full page. All these pages get saved into a permanent database called a page store.
So the page store is like the full library.
Think of it as the archive. Every single detail is coherently and inclusively preserved, just waiting for the researcher to come and retrieve it. The memo just tells the researcher where to start looking in that archive.
That dual structure is clever. You get the benefit of a quick index, the memo, without ever discarding the original source material in the page store. So a client comes in with a request, and now the researcher takes over. What's its core function?
The researcher addresses the client's request by performing what the paper calls deep research. And this isn't a single lookup. It's an iterative process, a loop, really, that's driven by the researcher's own LLM capacity.
A leap of what, exactly?
It involves three main operations, conducted over and over if needed. It starts with planning.
Okay, so how does it plan?
It uses chain-of-thought reasoning, grounded in that existing lightweight memory from the memorizer, and it analyzes what the user is actually asking for. It figures out if the answer is immediately available or if it needs to generate a concrete search plan.
So it maps out what to look for and where?
Precisely. And once it has that plan, it moves to the searching operation. The source material mentions the researcher has access to three distinct tools, which suggests one isn't enough.
Right. Why does it need three different search tools?
Because different tasks require different kinds of retrieval. First, it has an embedding model for vector search. That's for semantic retrieval, finding pages that are conceptually similar to the query, even if the keywords don't match at all.
And the second?
A BM25 retriever for keyword-based search. This is for your exact matching, looking for a specific name, a date, a product number.
And the third is an ID-based one.
Yes, an ID-based retriever, which allows for direct page exploration. This is useful when the memo structure points directly to a specific page index. Combining all three just ensures you get the best possible coverage and precision.
And then the loop concludes with reflection. It sounds like the system is acting as its own quality control.
It is. The researcher checks if the information it gathered actually satisfies the original request. If the result is incomplete or doesn't fully answer the question, the reflection step generates a new request to drive another round of deep research.
A whole new plan, search, and integrate cycle.
It keeps going. Only when the researcher is satisfied is the final result returned.
What's fascinating here is that this JIT architecture inherently provides advantages the AOT approach just couldn't touch. You're talking about high fidelity, task adaptability.
And domain generalizability, because the agent is building its own solution in real time, and the experiments absolutely confirm this. The researchers performed extensive studies comparing GAM against, well, every type of baseline, memory-free methods and other memory-based systems.
So after testing GAM across datasets like Locomo and Ruler, what was the bottom line? Was the performance improvement, modest, or was it really significant?
Oh, it was significant across the board. GAM consistently and substantially outperformed all the tested baselines.
All of them, even things like RAG and long LLMs.
Everything, from simple RAG and long LLMs to other complex memory systems like AMEM and MEMSIR. And crucially, the advantage was most stark in tasks that required multi-step retrieval and complex multi-hop reasoning.
Like connecting the dots across different memories.
Exactly. In the Ruler multi-hop tracing tasks, for example, where you need to connect several pieces of information across different pages, GAM achieved over 90% accuracy, while most of the baselines just failed almost completely.
Let's talk about those failures, because that tells us a lot about the core problem GAM solves. One surprising finding was about the performance of long context LLMs. Just increasing the token limit seems like the simplest solution to the memory problem. What did they find?
The performance of those long LLMs was distinctly underwhelming. Even when the context window, which was huge, 128K tokens, was long enough to fully cover the entire input context, the accuracy was still low.
Why would that be? Why would simply having the information in the context window not be enough?
Well, this aligns with a reported phenomenon that's sometimes called context rot or lost in the middle.
Right.
Simply extending the window isn't sufficient if the agent can't focus or filter the immense amount of potentially irrelevant information that's present. The sheer volume makes retrieval and reasoning unreliable. It shows that searchability is more important than capacity alone.
And what about retrieval augmented generation, or RAG? That's usually considered pretty robust. How did RAG handle these complex tasks?
Orgay's performance varied wildly. It did okay where the relevant information was, explicitly presented in a single, easily indexed document.
But not for the harder stuff.
But it struggled significantly in those multi-hop tracing and aggregation tasks. Again, in Ruler, the relevant information was non-obvious and scattered, and ARG is limited by its typically static retrieval step. If the initial search fails to bring in all the necessary context, the agent can't iteratively dig deeper.
Unlike the GAM researcher.
Exactly. It can't go back for a second look.
This brings us to what I found to be maybe the most critical insight: the difference in resource needs between the two agents within GAM. The researchers compared different LLM scales for the memorizer versus the researcher. What did they learn there?
They found a really crucial difference in model sensitivity. The researcher module is considerably more sensitive to the LLM's scale its capacity than the memorizer module is.
So the agent responsible for storing and compiling the history can be lightweight, but the agent responsible for thinking and searching needs significant muscle.
That's it, perfectly put. The memorizer maintains strong competitive performance even when it was downsized to the smallest tested model, the Quen 2.5 0.5b. Its job is essentially dynamic summarization and organization, which doesn't require massive reasoning power.
That the researcher.
But the researcher's performance deteriorated significantly when its backbone was reduced. The iterative planning, searching, and reflection required for that deep research, it just demands greater model capacity. This suggests the bottleneck isn't the storage, but the intelligence required to navigate that storage.
That model sensitivity is a huge design factor for deploying these systems. And since JAM is JIT, it also allows for test time scaling. You can throw more computation at a difficult query right when it arrives. Did more effort translate to better results?
It certainly did. They found that increasing the test time computation improved performance consistently. For example, increasing the maximum reflection depth, so how many times the researcher can loop back and check its own work, from 1 up to 5, yielded steady performance improvements.
And more retrieved pages help too.
Similarly, increasing the number of retrieved pages from 3 up to 20 also showed steady gains. This is a massive advantage. JAM can scale its effort dynamically, unlike the fixed workflows of the AOT baselines.
The ablation studies also seem to validate the whole architecture. What did they find when they tried testing the search tools in isolation?
Well, the best performance was only achieved by combining all 3 search tools,
Right.
the ID-based, the embedding, and the BM25 retrievers. It really validates the synergy you need to explore that page store.
And what about the modules?
Critically, when they ran a test using only the memory module, which is basically the equivalent of AOT compression, the results were the worst of all. It just reinforces that argument that pre-computed memory suffers from severe information loss.
And research, without the lightweight memory, without that index, also suffered.
It did. It led to a substantial performance drop compared with a complete GAM system. This just underscores how crucial that lightweight memo is for guiding the search process. The index is simple, but it's necessary for the researcher to know where to even begin its exploration.
So where does this all leave us? What does this mean for you as you watch the evolution of these AI agents?
I think the core takeaway is pretty clear.
The general agentic memory framework replaces that brittle, static, ahead-of-time compression with a resilient, dynamic, just-in-time process.
And that dual agent structure, the lightweight memorizer protecting the complete history in the page store, and the heavy lifting researcher performing that deep iterative research, it allows for context generation that is perfectly tailored to the immediate, often very complex task.
The research seems to back it up.
It does. The research validates GAM's significant effectiveness in preserving that fine-grained historical information and optimizing task completion, especially in those areas where traditional methods that rely on pre-summarization just fail.
And as you think about how these agent systems will be built in the future, it's worth remembering that crucial sensitivity finding. The research showed that the memorizer, the archiver, can be built on a very lightweight model, but the researcher, the planner, the searcher, the reflector, is hungry for LLM scale and capacity.
Which is a very important distinction.
It is, and it raises the question of whether the true bottleneck in advanced agent intelligence is not the ability to store the memory, but the capacity required to intelligently plan and execute the search of that complete history database.